Good afternoon and welcome again. Many of you have had to hear me introduce 2 talks now, so I'll keep it short. My name is Dan Parrish. I work in the Office of Alumni Relations, and very excited to see you all coming in and joining us on a beautiful, beautiful afternoon. Many of you were here yesterday, and I promised that the temperature was headed the right direction and the weather was headed the right direction, and I'm glad that that came through. I'm glad we could deliver that for you, so I hope that that will stay true for the rest of your visit in Hanover. You heard the announcement earlier, so just another reminder, please make sure your cell phones are silenced. Also, as you go through this weekend, you know, if there are, through your reunion, if you have feedback for us on any of the programming, the panel we had yesterday, the lectures that your classes have arranged, definitely let us know in the survey that will be sent to you after reunions. We want to make sure that we can respond to your interests and make sure that we make all this work for you. So without any further ado, let me introduce today's speaker. We're very, very happy that you've joined us for this discussion of breaking the neural code. And I'm very, very happy to introduce Professor James Haxby. Jim Haxby is the Evans Family Distinguished Professor and Director of the Center for Cognitive Neuroscience at Dartmouth. And the members of the class of 1961 will know that the Center for Cognitive Neuroscience was founded in the 1990s by your classmate, Mike Gazzaniga, who is somewhere in Europe presenting at a conference right now. So I'm sorry he's not with you, but I'm glad that we can have Jim Haxby here to talk about the work that Mike started here at Dartmouth and the work that he's carried on to new levels. Professor Haxby is also the most frequently cited scientist in the School of Arts and Sciences at Dartmouth. Before coming to Dartmouth in 2008, Dr. Haxby was a professor at Princeton University and a research scientist and section chief at the National Institutes of Health Intramural Research Program. He is a founding officer and former chair of the International Organization on Human Brain Mapping. His research uses functional brain imaging to investigate the organization of the human brain. In 2001, he published a pioneering paper that showed for the first time that brain activity could be decoded non-invasively in humans using functional brain imaging. I understand very little of that, and I'm excited that he's going to explain it to you. His work has been recognized by the Cognitive Neuroscience Society on several occasions, including his recent receipt of the Kavli Distinguished Career Contributions Award. Please join me in welcoming Dr. Haxby to the stage. Thanks very much.
Well, I want to thank everyone for coming into this dark auditorium on such a beautiful sunny afternoon, especially after the string of bad weather we've had before this. Now, and I'd like to thank the Alumni Office for giving me the opportunity to talk to you and try to explain what is a neural code and what could we possibly mean by cracking the neural code. And I hope that, I hope to be successful. This is a different kind of talk for me. I'm usually giving very technical talks at scientific meetings, and I have no anxiety when I give one of these very technical talks at a scientific meeting. But trying to talk to you is a greater challenge. So what is this neural code? What are we talking about? What does that mean? Neural refers to brain activity. And what's this code? Well, we can measure patterns of brain activity. And there are a variety of ways to do that, including in humans using functional brain imaging. And these patterns of activity and connections, they encode the contents of our thoughts, experiences, decisions, emotions, even our knowledge, the contents of mind that make us human and unique individuals and members of our community. The neural code is the basis of our mental lives and our culture. So we think this is a big deal. And we think that the understanding the neural code, which we're actually making serious progress on these days, is going to have a profound effect on the academy and culture. So breaking the neural code means developing computational methods that translate brain activity patterns into the information that is represented by those patterns. So what could that possibly mean? How is it possible to do this kind of decoding? How close are we? What are the implications of that? Well, let's start with science fiction, because I think what I'm talking about today is pretty close to science fiction. And go back to a movie, I think this came out in 2001, was based on a Philip K. Dick science fiction novel. Philip K. Dick was the inspiration. Many of his stories were used for blockbuster Hollywood movies like The Minority Report and Blade Runner, Total Recall, some of my favorite movies. Now, in The Minority Report, there are these people called precogs. So they're lying in this bath of warm water, and they have these sensors on their head that you can just barely see that are reading out their brain activity. And these people have visions of crimes that will be committed. And so the idea in this future that Philip K. Dick described is these brain sensors measure their patterns of brain activity. And what do they do with them? They read them out so they can see the visions that the precogs are having. And who reads them out? It's Tom Cruise. So here's Tom Cruise, and he's putting their images up on the screen. And then at this point, he sees a crime about to be committed in the future, and they send out the police to stop the crime before it happens. So this eliminates crime in the future. So it's a wonderful story. It's science fiction. So the idea is you can read brain activity, and from that activity, understand what the person's thoughts are. This is science fiction, or is it? And so what really my talk is, in a sense, it's an update on the Minority Report. What is the state of the art now for reading out people's brain activity? So before I get into that, I want to just make a few comments about why this is an area of emphasis for Dartmouth. And one of the main reasons an area of emphasis is because of someone I suspect many of you know, who is Mike Gazzaniga from the class of '61. And he's a bigger-than-life character, and he was the founder of the Center for Cognitive Neuroscience. He was the one who got the first MRI scanner here on campus. We were the first school in the country, in the world, to have an MRI scanner in an academic department dedicated to research. Now, you may remember him a little bit better like this. This is his picture from the yearbook when he graduated from Dartmouth. And this is a picture when he was a student at Caltech, working with Roger Sperry. So Gazzaniga made Dartmouth the birthplace of cognitive neuroscience. This really is the place where cognitive neuroscience started. And this is a story that, of how the name cognitive neuroscience came to be. So here we have a neuroscientist, Mike Gazzaniga, and the great cognitive neuropsychologist, George Miller, were on the way to a dinner meeting at the Algonquin Hotel. They were joining forces to study how the brain enables the mind, a subject in need of a name. Out of that taxi ride came the term cognitive neuroscience, which took hold in the scientific community. So it all came from a taxi cab ride, Mike Gazzaniga and George Miller. Since then, Gazzaniga started the Center for Cognitive Neuroscience at Dartmouth, which I'm now the director. He founded the Journal of Cognitive Neuroscience. He founded the Cognitive Neuroscience Society. So this really is the birthplace of this movement. And we continue to be world leaders in this area. And now, since then, I became the director in 2008. We've been holding international workshops on neural decoding here at Dartmouth. And our hiring right now, our junior faculty in computational neuroscience is focusing on these young people who are really the future of the field, like Ali Reza Soltani, Matt Vandermeer, Luke Cheng, and Jeremy Manning. So what are patterns of brain activity? What are we talking about? And how can these patterns be decoded? So let's first talk about a pattern of brain activity. And let's go way down on the evolutionary scale to the zebrafish larva. So this is a zebrafish larva, pretty unimpressive little animal, but the important thing about this is it's transparent. So you can look right into its brain. And so what scientists have done is they've created genetically modified zebrafish larvae so that their brains produce a protein that fluoresces, shines when a neuron is active. And this is the result. So this is a video of activity in the zebrafish brain. So this is the zebrafish brain here. This is the front, this is the front, this is the back. And each point here, each one of these little points is a single neuron. So with this technique, they can measure the ongoing activity in every single neuron in the zebrafish brain in real time. And so the people who are doing this work, every hour, they collect 1 terabyte of data, and they're having a difficult time learning how to deal with that. Now, the zebrafish brain has about 100,000 neurons. The human brain has about 100 billion, so 1 million times more neurons. And human skulls are not transparent. So we can't genetically modify our undergraduates and directly measure their brain activity in the same way. So we have to have a different method for measuring brain activity in the human brain. Now, this is from a medieval etching that looks kind of like a scanner. And this is information about brain activity. These are actually, this is supposed to be fantasy coming out of this person's head that's been put in this kind of oven-like thing. Well, the modern version of that is the MRI scanner. So this is the MRI scanner. This is the state-of-the-art machine. We're getting one of these this summer. It's arriving. We took out the old scanner about a week ago, and this new scanner will be installed in July. This is a Siemens Prisma 3 Tesla MRI scanner. The way this works is we have people inside the scanner, so their head's inside, and using MRI, we measure a signal that reflects blood flow, actually blood oxygenation. And that turns out to be a very good index of how active a small location in the brain is. So we measure patterns of brain activity in human brains using MRI. There are other ways to measure brain activity in humans that are non-invasive, like MEG. This is an MEG machine here over on the right. Looks like a giant hair dryer. And then there are very invasive ways to measure brain activity, like electrocorticography, where electrodes are placed directly on the cortical surface in patients who are undergoing treatment for epilepsy. And we actually have an ECOG group at Dartmouth Hitchcock Medical Center that we collaborate with. So here are patterns of brain activity that we measured with MRI. This was actually a long time ago. So this is the pattern of activity in one subject's brain while she looked at faces. This is a pattern that she produced when she was looking at houses. This is the pattern she produced when she was looking at chairs. And this is the pattern that her brain produced when she was looking at shoes. Now you can see these are distinctively different. Can we tell anything from these patterns of brain activity? So what we did is in the same subject, we got independent scan while she was looking at some category, category X. And we asked, can we tell what category of objects is she looking at when her brain was in this state, produced this pattern of activity? So this is a guessing game. Can you guess? What was she looking at? What is category X? Looks like faces, doesn't it? In fact, it's hard to tell what the difference here is, even though these data were from different scans from these. And she was looking at faces. Now here's the other two categories are a little bit, it was less likely. In fact, at the time that we published this paper in 2001, no one thought we would ever find a difference between the activity for two man-made objects like chairs and shoes. But we do have differences here. And so this category Q is either for chairs or shoes. It's another guessing game. Can you guess which one it is? And it is. So you can see this by eye. This is quite obvious that the pattern of activity is changing depending on what kind of experience the subject is having, the visual experience in this case. So in this study, which really got the field of neural decoding in humans started, we could decode which of 8 categories the subjects were viewing with over 90% accuracy. So chances about 12.5%. So this was a very surprising result. Now since then, we've gone to different kinds of stimuli. So we have people watching a movie. Does anybody recognize this movie? This is from the beginning of Indiana Jones and the Temple of the Lost Ark. So we have people watching this movie, and we measure their brain activity while they watch it. So these are patterns of brain activity in two different subjects while they're watching this movie. And you can see just how daunting this problem is, because this pattern of activity is synchronized with this pattern of activity. So it's representing the same visual information, but it's hard to see what the commonality is. Well, we figured out how to detect that commonality, and using that, we now can decode what part of the movie somebody is watching. So we have someone watch the whole movie, and we take out 15 seconds of brain data. We say, can we tell what part of the movie they were watching from the brain data, from their brain, what their brain was doing while they were watching that, as compared to the entire rest of the movie. So this is now 1 out of actually 1,300 classifications. So chance is less than 0.1%. But we can decode exactly which segment they're watching with over 93% accuracy. So there's a tremendous amount of information in these patterns of brain activity that's very specific and picks up very subtle differences, not only in visual stimuli, but also in auditory stimuli, also in cognitive states like intentions. Now, in that study, we would decode what the subject was watching from that movie. Now, in Jack Gallant's laboratory at Berkeley, University of California, Berkeley, they've developed a system now where they measure people's brain activity while they're watching a movie clip, and you can see how varied these are. So here's Steve Martin, and here's some text, and here's an ink blot growing, and here's Steve Martin again. He has something for Steve Martin, elephant. So what they do is they measure the people's patterns of brain activity, and then from the pattern of brain activity, they try to recreate the movie itself. So this is really a direct analog to what Tom Cruise was doing in the Minority Report. They are reproducing a movie based only on the brain data. And the results are over here. So here's Steve Martin, and the reconstructed movie is over here. Here's an elephant moving. This is a big dark blob moving. So it's not like Tom Cruise yet, but this is just the first stab at that. So they're able to make movies that really have a lot of the visual features. Here's this woman talking. There's a face over there. There's Steve Martin moving, et cetera. So it's getting to the point where it's now possible to recreate the experience that someone is having from their brain activity using neural decoding. Now, this, again, is a slide that shows how electrodes are placed on the cortical surface in patients undergoing surgery, brain surgery, for planning epilepsy surgery, planning surgical treatment. Now, in this study, what the people did is they had the subjects listen to words, and then they measured their brain activity using this other technique, ECOG, and from the patterns of activity that they measured in language cortex in the left hemisphere, they built a model so that they could then produce a sound file that was their best prediction of what that pattern of brain activity corresponded to in the subject's real experience. And let me play this for you. What you're going to hear is the word that they heard, Waldo, okay, and then followed by the reconstructed sound, reconstructed based on brain activity, using two different models, a linear and a nonlinear reconstruction. And then it goes through the other words, structure, town, doubt, property, and pencil. Now, don't expect this to be Tom Cruise, but just remember we're at the early stages here. Oops.
Waldo, Structure.
Town. Doubt.
Property. Pencil.
So it sounds kind of like someone is trying to say these words from underwater in the bathtub. But still, it's recognizable. It's recognizably distinct. So what could this be good for? Well, imagine someone who has a disease like Lou Gehrig's disease, amyotrophic lateral sclerosis, who's unable to speak because of paralysis. And we know from communication devices that these patients have intact intelligence and can communicate if somehow they can get the signal out. Well, it's conceivable that their brain activity could be directly decoded to drive a speech synthesis device, allowing people with Lou Gehrig's disease to speak. Now, that doesn't exist yet, but I think this is a demonstration that that kind of thing actually is feasible. Now, this is from work by Andy Schwartz at the University of Pittsburgh. And he did the work first in monkeys. There's a monkey over here, and his arm is in this tube that restricts its movement over here. And this arm that you see is a robotic arm. So in this experiment, they are measuring the monkey's brain activity using electrodes placed in the cortex, the brain cortex, and decoding the monkey's intention to move. And the monkey has learned to operate the robotic arm so it can reach out, grab a piece of marshmallow, bring it back, and feed himself. So this monkey is moving the arm with that kind of articulated, purposeful movement simply by thinking about what it wants to do. Now, this is a woman who has a progressive neurodegenerative disease and is completely paralyzed. She can speak, but she can't move her legs or arms. And she agreed to let these people put electrodes in her brain. And here she is, operating a robotic arm with a chocolate bar, bring the chocolate bar to her mouth. Again, she is operating this robotic arm solely through thought. How does that work? So there was a piece on 60 Minutes a few years back about this
After
woman.
the surgery,
And I want
we
to play
came
this for
back
you.
to see whether she would be able to control the robotic arm with nothing but her thoughts. They plugged her brain into the computer, and this is what we saw.
I can move it up and straight down and left and right and diagonally. I can close it and open it, and I can go forward and back.
That is just the most astounding thing I've ever seen. Can we shake hands?
Sure.
No, really.
Yeah.
Like, come right over here?
Yes, you come over
Okay.
there. Let me grasp your hand there. There we go.
Oh, my goodness. Wow.
And I can do a fist bump if you'd like.
That's amazing. What are you doing, Jan? What's going on in your mind as you're moving this arm around? What are you thinking?
Okay, the best way to explain it is raise your arm.
Uh-huh.
Go. Now,
Right.
what did you think about when you did that?
Well, not very much. I do it all the time.
Exactly. It's automatic.
So that's pretty impressive. For her, moving this robotic arm for these purposeful actions is as automatic as if it were her own arm, which suggests that they're really getting pretty close to what the neural code is for guiding movement. So this project is in progress. There isn't a practical, brain-driven prosthetic device that is in wide use yet. But these are proofs of concept that this thing can work. They're encountering big problems, of course. And much of that is because you need sensory feedback. When we move, the sensory feedback that we get from our arm is very important for coordinated movement, smooth coordinated movement. And so they have to build that in. So they're working on it, but they're getting close. So the question is, so I've shown you that the neural code, whatever this is, these patterns of brain activity, can be decoded, and they can be decoded in interesting ways to understand visual perception, to recreate visual experiences, to recreate auditory experiences, and to guide motor movements. But what is this neural code? So, well, let's go talk about some other codes. Language is the code we know best. We all use language every day. And it's a symbolic code to convey ideas. This is the Rosetta Stone. It was discovered in 1799. Up here, this is a decree by a pharaoh that was inscribed in hieroglyphics, in Demotic script, and ancient Greek here. This was the breakthrough that allowed Egyptologists to decipher the hieroglyphics that they were finding in Egypt, because they could find the correspondence between the hieroglyphics here and the ancient Greek, which was well understood. So that's an instance of decoding hieroglyphics, which is a language code. Here's another code. These are secret codes that encrypt military communications. This is the Enigma machine. This was used by the Nazis for all of their military communications. And they thought they had perfectly secure communications. But then some cryptologists, first some Polish cryptologists and then Alan Turing in England, figured out how to decode the messages that were being encoded by this Enigma machine. Now, another code that we all know is the genetic code. This encodes the sequences of amino acids to build proteins. And this was figured out in the 50s and 60s. And the first paper that described the code itself came out in 1961. So in this genetic code, there are sequences of 3 neural bases, AUG, adenine, uracil, guanine, and that's called a codon. And that codon corresponds to a specific amino acid. So this sequence of codons corresponds to a specific sequence of amino acids, and that's how proteins are built. So this is a 4-letter alphabet, basically. And this 4-letter alphabet, the genetic code, specifies how all proteins are made, and it specifies who we are, how our brains are made, how our bodies are made, why are we different from monkeys, why are we different from cats, and why are we different from frogs. We all have DNA, but all animals are producing proteins, but our proteins are very specific to making us human. So this was a very important breakthrough, and the simple elegance of this of the code, just a 4-letter code, encodes all this information. So what about the neural code? Well, the neural code, I would argue, is much more complicated than the genetic code. And the neural code doesn't just encode sequences of amino acids for proteins. It's encoding experience, language, thoughts, emotion, knowledge, decisions, all the mental contents that make us human, that make us unique individuals. But how does it do that? I mean, is this a problem that we can address? So I want to back up and talk a little bit, I apologize, about visual neuroscience. And this is a figure of the organization of visual cortex in the monkey brain. It was published in a paper in 1991. So all the areas shown in color are visual areas. So you can see in the monkey brain, the visual areas cover about half of the cortex. They're highly visual animals. Humans, in the human brain, visual cortex covers about 1/3 of the visual cortex. We're highly visual also. But there's something curious about this. There's not just a visual area. There's a sequence of visual areas. V1 is the first visual area, then there's V2, and there's a V3, and a V4, and a PIT, CIT, MT, 7A, LIP, VIP. What's going on here, okay? So this is the kind of thing that neuroscientists discover, and they describe it, and then they really don't know how it works. And then but then the puzzle is, let's figure out if we can figure out how it works. Well, in the same paper, they published a meta-analysis of all the connections that had been described between these brain areas. So there are about 30 or so brain areas here. Now, this is the wiring diagram for how these brain areas are connected. And you can see it's really complicated. It's worse than the New York subway map. And it starts off with the early visual areas here, V1 to V2. And then there are areas over here for object vision, areas over here for spatial vision, et cetera. And everything seems to be connected to everything, and it's really hard to figure out. Well, this actually was the inspiration for people trying to develop machine learning systems, machine vision systems. So this is, how do you program a computer to do the kind of visual object recognition that humans can do so easily? So this is another way of thinking about the visual system in the primate brain. So these are the same areas that I just showed you. And you can think about these as different layers in a processing pathway. And the connection goes from early visual cortex, V1. This is the retina. This is in the thalamus. There's V1, V2, V4, et cetera. So there's a sequence of areas that get visual information from the previous area and send information on. So there's a sequence of processing steps. Now, frankly, the people doing machine vision didn't understand why the brain would have so many layers, because they thought it could all be done in a single step. You just need to get the visual input. Then in a single step, you convert that to recognition of what is in the image. But they were wrong. And then this knowledge about the neural visual system inspired the development of machine vision systems here that are called deep neural networks. So this is the neural representational spaces in different brain areas. And this is in vivo. And then this is the machine vision system. Okay? And so there are different layers. That's why it's deep. It's a multiple layer system. Okay. So what does that mean? What do deep neural networks get us? Well, how well do they work? They work really, really well. This has been a revolution in machine vision. So identifying objects now with trained neural networks, trained deep neural networks, approaches human performance. In this one study by Teigman et al., they just looked at face recognition, recognizing the identity of faces. And again, they have multiple layers here in their deep neural network. And then they identify whose face they think it is. And the performance of this system, it really equals human performance. So now machine vision systems are up to human performance in visual recognition, some would argue. I think they've got a ways to go, but they're making tremendous progress. What else are deep neural networks good for? Well, the deep neural networks, it's a mathematical system. You can have different kinds of input. The input doesn't have to be a visual image. It could also be an auditory file. It could be a movie, things like that. So this is from Google's website. This is their cloud speech application program interface, okay? What does this thing do? It converts audio to text. So it can take any speech input and convert it to words. How does it do it? Applying powerful neural network models. This is the same math, okay? Which is based on how the brain processes information. Now, not only that, but this API recognizes over 80 languages and variants. So it does Welsh, it does Urdu, it does Vietnamese. How many of us have 80 languages under our belt? And anybody can integrate this into their own app. This year, a computer beat the world Go master. The Go Master is that Japanese game that some people say is more complicated than chess. And the computer beat the World Go Master this year. How did it do it? Using deep neural networks. So this is using the same kind of machine intelligence system, this time not for speech, this time for analyzing the strategic configuration of a game, and won. So as this article was written by Christoph Koch in Scientific American, and it says this is a decisive step on the road to overtaking the natural variety of intelligence. Elon Musk. I don't know how many of you are fans of Elon Musk. I'm a huge fan of Elon Musk and his Tesla machine. He's kind of the mad genius of Silicon Valley with a vision. But he's producing real electric cars that work, and these real cars can drive themselves on the highway now. And he says that in 2 years, they're going to be fully autonomous. So in other words, if the regulators allow it, you could ask your car to come pick you up at work, and it will drive up to the entrance and pick you up. They think that companies like Uber will be able to have driverless cars doing this. So how is this possible? How can you get a car to drive itself? This is a complicated procedure. I remember teaching my son how to drive and how difficult it was for him to learn at first. And at one point, we ended up on the neighbor's front lawn. So this is not a trivial task, driving a car and taking into account everything that's going on around and staying safe. It's done with deep neural networks. So these are very powerful systems that are inspired by the neural representational spaces that are studied in vivo in brains, in the primate brain and the human brain. And so the inspiration has been to develop deep neural networks. At the same time, these deep neural networks are now providing models of objects and faces and speech that we can now test. We can now try to model the neural representational spaces. So we're getting much better models of how the brain is organized by testing to what extent the brain mimics what these machine vision systems do. So our understanding of the brain, actually right now, at this very moment, the last year, 2 years, the rate of progress in understanding the neural code for vision has just been breathtaking. And largely because of the application of this deep neural network architecture for modeling this images. So as we understand the brain better, helped by these models, deep neural networks, which is neural networks in silica. These are neural networks in vivo. We're going to learn more. So this is the slide that I showed before with the deep neural network and the brain network. Now you'll notice here that these transitions from V1 to V2, V2 to V4, V4 to PIT, CIT, and AIT, these are circles with little question marks in them. We don't know what these transitions are, how information in this representational space gets translated to this representation, and finally to a representation that starts to categorize and distinguish objects. But in the model, we have an explicit model now of what these translations are. This LN stands for linear nonlinear transformation. So we now have specific models for how this processing is occurring. And as we have a specific model, then we can go deeper and understand better what the in vivo brain system is actually doing. So this is a closed loop, or this is a positive feedback cycle. So the study of the brain code in vivo inspires development of these machine vision systems. And the machine vision systems help us design better experiments and make better models of what's going on in the brain. And this, again, is an area that's really working these days. So what do these machine neural codes add to the text or images or sounds or videos? What they add is meaning, okay? So if you just have a text, like a book, okay? All the information you want is in the book, but it only becomes real in the interaction with us when we read it. The book by itself doesn't have any, it doesn't really have that meaning. But these neural codes, these machine neural codes, add that meaning in these deep layers. They distinguish objects, they distinguish sounds, they link sounds to words. More models link words to meaning, link sequences of words, sentences to stories. And so the models themselves now have this meaning of what is the object, what is the story, what are the qualities of the music that make it sound like music. So here's an example. This is a paper that just came out in April 2016, again from Jack Gallant's group at UC Berkeley. And they now have produced a map of how word meaning is represented in the brain. And with this model, you can go on their website and you can say, show me the pattern of brain activity for platypus. And it's going to show you what the brain activity pattern would be for platypus. Say, okay, well, show me the Eiffel Tower. So there now is a working system. Now, this is a primitive model. Don't get me wrong. We haven't caught up to Philip K. Dick yet. But this is showing that it's now possible to study in the neural code very high-level information, the meanings of words. Now, the subjects in this study didn't just look at words. They listened to stories. They listened to stories from the Moth Radio Hour. And then analyzed how their brain patterns changed in the words in that natural speech at normal speed. So, how will the neural code, both in viva and in silico, be used in the future? We don't know, okay? We don't know. We can't predict the future. We can make guesses, but the use of the genetic code, when people were first figuring out what the genetic code was and how to manipulate it in bacteria, there was no idea that it would turn into a multi-billion-dollar industry. And we don't really know what the neural code, understanding the neural code will do either. I mean, we can make some guesses. We can think about medical applications. So these brain-driven prostheses for movement and speech, we've shown that that's possible. We might be able to better understand the neural basis of disturbed reality testing in schizophrenia, or disturbed social cognition in autism. Maybe there's applications in education. We can study how learning alters the neural code. If someone learns something new, like the principles of physics, how is the neural code for physics changed by that learning experience? And what's the difference between people who learn those physics principles well and learn them poorly? This actually is a study that's going on right now at Dartmouth by David Kramer in the education department. This might help guide the development of new teaching methods. It may be useful in the humanities. We can now map out the meanings of words. Can we map out the meanings of stories? Can we start to understand how the brain encodes the narrative structure and the personalities and characters and interactions between people in a Jane Austen novel? Can we understand music better by understanding how the brain processes that music to appreciate its qualities? So all these are possible applications. Then there are sillier things that might be possible. It might be possible to build a lie detector. It might be possible to do a better job of judging people's preferences and do a better job of targeting advertisements or designing advertisements to be more effective. We don't know. But I think that it's bigger than that. It's much bigger, because this neural code, as I said, this is the basis of our mental lives. This is the basis of our knowledge. This is the basis of our culture. So it's really a universal code And we're now developing machine intelligence systems, machine learning systems, to build these neural codes for specific applications like speech to text or playing Go. But this is a very active field, and there are a lot of people who are, thousands and thousands of people working in this. As a matter of fact, as an aside, the person who developed deep neural networks, Jeff Hinton at the University of Toronto, was bought by Google. So Google, he still has this position at the University of Toronto, but Google realizes what the potential of these are. And I have no idea what he's being paid, but I bet it's not a small salary. So this universal code is different from the codes that we now use, like text in books, or images in movies, notes in music. So all of these things, like literature, movies, images, music, lectures, all these things will be translated as this neural code becomes more sophisticated into this universal basis. And this will allow us to translate across languages, communicate across languages better. It will allow us to interact more effectively with the machines themselves if the machine uses the neural code that is based on the neural code that we understand. Now, Elon Musk, again, with another one of his crazy statements that he came out with a few weeks ago, was that computers are going to become so complicated and sophisticated that in order to interact properly with them, people will have to have computer devices implanted in their skulls. I think he may have gone too far with that one, and we don't know how that would work. But this involves understanding, how a computer chip could interface with the neural code. So the world's libraries and archives of movies and images and music will be translated into this neural code, and that will amplify these materials with meaning, and will be a much richer format than just the original text or music sheets or audio files. With that, I'd like to thank you for your attention, and I'm happy to answer whatever questions you might have.
I was just curious, when you showed us the patterns that the brain produces when it sees a picture, what about the emotional content that goes with that picture? If the person looking is sad or happy as a result of that image, does it affect the imaging, and how does that come through?
Yeah, so the facial expression that conveys emotion can also be decoded from brain activity in a different part of the brain from the one I was showing you. So that's associated with patterns. And emotion is another type of information, just like you say. The person could be sad or happy or puzzled or dismissive. I mean, there's many shades of emotion in people's responses. And that's another area for neural decoding research. So one of our junior faculty, who is very computational, he is tackling that, how to decode emotion from brain patterns. Use the mic, please. My hearing's terrible, so I need you on the mic too.
I've read several books within the last 5 years on the intersection of physiology and magicians, and their use of misdirection and things to trick the mind and so forth. Have you been doing any kind of work of that nature, or is that not taking place in what you're doing here at Dartmouth?
Yeah. So magicians can do things that seem magical because they're very good at making you look one place when they do something quickly someplace else. And This has to do, actually, it's an active area of research. And the idea is that when we experience something, we really are only processing part of the signal that's coming in because we have capacity limitations. We can't process everything. But we have this experience that we're experiencing everything. So when I look at you, I have the experience of the entire auditorium and all those people out there. But what it appears to be is that that experience of the full room with all the people is, in a sense, an illusion because I can predict it. I know where I've seen everybody out there, so nothing is happening that makes me think that my prediction is wrong. So I have the experience of everyone's out there, but I don't. It's actually just a prediction of what I already know. And magicians take advantage of that because they change something without you noticing it, and because we are predictive machines, we predict what we expect to see next. We predict that your watch is still on your wrist or whatever, right? And then you find out the person's holding your watch like this.
Very famous case of the gorilla running across the stage and nobody sees him.
Nobody sees the gorilla, even though it's, once you know it's there, you can't not see him, right? But this is a famous video in which they have people playing a game where they're passing a ball to each other, and the task is you have to keep track of who's got the ball. And so you're watching the ball, and then, unbeknownst to you, somebody in a black gorilla suit comes out and walks through the crowd of people playing the game. And nobody sees the black gorilla because everyone's concentrating on the ball. And that's because that was a very low probability event. It's not something that you would predict. So you miss it.
Are you doing anything in this area at all here at Dartmouth?
No, we're not. I'm not doing anything personally. There are people. And we actually have a workshop this summer on predictive coding, which is this idea that much of our experience, our mental life, has to do with predicting what's coming next, so that we only have to process what's changed.
This question is motivated by the last slide that you put up about future applications and practical applications. If you talk to a physician who is a specialist in ALS or Parkinson's, they will say that we have no solution, we have no way to eliminate that disease from a person because we don't know what causes it. Is there anything that you're doing that would permit the repair of the central nervous system that would give rise to a solution for people that have ALS or Parkinson's?
I wish. I really wish that we were part of that effort to find solutions to the progressive degeneration in those diseases, but we're not. All that we're talking about here is ways to reduce the devastation of the symptoms by allowing people to speak or move.
Maybe this is more along the lines of science fiction, but would there be a way that these wonderful neural in silica things we could go to a vending machine and pick your course at Dartmouth and take all those patterns and put them in our head?
We're not there yet. But there are people who are working on sensory systems that then have electrodes in the brain to induce a pattern of activity based on the visual input to a video camera. This is very primitive, but it does allow people to have some visual recognition. And there are people who are blind who have been willing to have these electrodes implanted to try that. So, again, I think this is decades away, but it's not impossible. So it's conceivable that there could be a device that could help you to speak a foreign language, right? Or understand a foreign language. I don't know, but it's not inconceivable that some abilities could be transmitted by something like what you're talking about. But that's a long ways away. It worries me.
Jim, we'll do one last question.
Okay.
With regard to the images that you presented to persons, to what extent is there variation among individuals seeing the same image, and to what extent is there variation within one individual across time and being presented with the same image?
That's such a good question. As scientists, we start off by making the problems simple, and then once we get the simple answers, we go to the more complex questions like yours. So the first studies assumed that our responses to our brain patterns for an object was the same every time we have that experience. But we know that's not true. And we know these things change with learning, they change with attention. And so building that into our models is something that people are doing now. But it's definitely true that there is change over time. Now, there's also temporal information in something like speech processing, because speech is inherently a dynamic process that unfolds over time. So the patterns of activity are tracking those changes and are somehow integrated into words and phrases and meaning. It's a challenge.
Thank you very much, Jim, and we look forward to coming back in 5 years and hearing what's come next. This is
We're
really
going to have
great.
that vending machine ready in 5 years.
That's right. The vending machine will be here in 5 years. Please join me in thanking